thank you everybody for coming. So I was saying before, I gave a lot of virtual talks in 2021, but it's been a while, so hopefully I remember how to do this. And yeah, Thayer is here to answer all of your questions, so I'll just direct them all towards him. No, that's you can certainly interrupt and ask questions. It's fine. So this is a case. Let me just say a few words before getting started. So this is a case where if you if you haven't read the paper that was sent around or looked at the most current one that's on my website, that's probably actually a good thing because this is going to be a bit different than what is up there. So as Mary mentioned, we got a revision request, different not only in the content, but also even the number of authors. So we got a revision from Econometrica, and one of their big requests was that we needed an empirical application, and Thayer and I are not data people, to say the least. So Gaurab agreed to join us and do the empirical side of things. So I'm not going to show you any of that today. I'll make some allusions to it, but that's still kind of work in progress. But so right now, even the theory, though, our referees also had some pretty good comments about the theory. So even the theory that I'm going to present to you is different than the most recent, publicly available version. So if you go after the talk and look at my website and you see that it's different, that's because it is different, and just kind of wait a couple of weeks. We don't have quite the polished draft yet to post, but hopefully soon we'll have that. So, all right, with that all said, let me kind of jump in and let's talk about rankings. So just that by way of motivation, I probably don't need to really motivate this, but rankings are important. So we consult rankings all the time. I'm not sure how things work in Europe, but in the US, we have this thing called the US News and World Report ranking of colleges, which every year this magazine that was a print magazine that was popular, I think, probably 70s, 80s, and now it's essentially defunct. Except the only thing they do is they continue to publish a ranking of the colleges every year. And these rankings are like a really big deal. It's the only thing keeping this magazine afloat. Students care about them. Colleges really care about them. So they're a very important part of the college admissions process over here in the States. But not only in colleges, in academia, we care about rankings of journals. If you're a family looking with school-age children, you might care about elementary school rankings. So our very broad research question is just how should we construct these rankings? I'm going to, of course, pin that down. But let me just, talk a second about this sort of the typical approach, which is kind of this US News approach, is we collect some data to proxy for quality, and then we have some formula that we use, throw it all in, and we get out an index, right? So one problem with US News is that it's sort of famously opaque. They don't tell you exactly what goes in there. They tell you some of the inputs like acceptance rates and yield rates and SAT scores and whatever, but I think they also have some kind of fudge factors that they kind of throw in and they kind of keep it hidden. For journals, we often measure them by things like acceptance rates, citation counts, stuff like that. And if you've ever heard of this kind of well-known aphorism that goes by the name of Goodhart's Law, which is when a measure becomes a target, right, it ceases to be a good measure, right? If people know what goes into the formula, then what are they going to do? They're going to try and sort of target what goes into the formula, right? And indeed, at least in the college case, this is exactly what happens. There's plenty of evidence that colleges do try to strategically manipulate these rankings. So they want lower acceptance rates. So what do? They buy up all kinds of student data and they solicit applications from people they know they're going to reject, right? They want higher yield rates for the US News ranking. So yield is the percent of people who are admitted who enroll, who choose you over everyone else. So what do? They strategically reject applicants they expect to reject them, right? Even if they're very good students, they might still be rejected because I think that they're going to go somewhere else anyway, and so I'm not going to admit them. And in journals, there's also well-known strategies that editors use for inflating impact factors. So this is more in sort of the science medical literature, but there's all kinds of strategies there too. So what we're going to do, rather than use as kind of objective, proxies for quality, we're going to take a different approach, but it's going to be a familiar one, at least to an economist. And it's going to be familiar because what we're going to try and do is we're going to seek to rank institutions based on the agent preferences. So the student preferences or the researcher preferences. And so this should sound kind of like, an arrow impossibility type problem, right? What was the environment arrow was considering? We have a bunch of agents who rank a bunch of alternatives, and I want to output a social ranking, right? That's basically what we're going to try and do with colleges. Now, of course, we're not going to, get around the impossibility theorem. We're going to go in a different direction, fairly quickly. But that is the sort of flavor of the problem that we are going to consider. Okay. So what I'm going to do today is I'll give you some axioms for preference-based rankings. They're going to be very different from the arrow axioms. We call them, they go by the name desirable rankings, hence the name of the paper. I'll give you some algorithms to construct these rankings. I'll show that these rankings are correct in the sense that they converge to the correct rank as the market grows large. I'll back that up with some simulation evidence. And like I said, not today, but a work in progress that we're working on is an empirical application where we're actually we have data from Chilean colleges. So in Chile, what they do is they have kind of a centralized deferred acceptance style assignment mechanism where all the students rank all the colleges, and then they use deferred acceptance to make an assignment. And that's basically exactly the data that we need to compute our ranking. So we're in the process of doing that, but I won't have those results for you today. That's still in progress. Okay. All right. So like I said, this preference aggregation is kind of a classic question. We're going to do things a bit differently than Arrow did, so a few things that are going to be different. One, we're not going to seek a strict ranking, but we're only going to seek a partition. So we're going to divide colleges into tiers, kind of the top tier colleges, then sort of the middle tier colleges, the low tier colleges, etc. And another important distinction is that, in Arrow, what's he doing? He has a bunch of alternatives, and they're just sort of like, passive alternatives, different, outcomes to be ranked. But in our case, a college is an alternative, but it's not passive. Colleges actually select students, right? And what that means is that in our setting, there's going to be an assignment or of students to colleges. So every student is going to, accept or be matched with one college. And so there's some process, some college assignment process, and that outputs a matching. And we're going to use this matching, which I'm going to call mu down here. That's going to denote the matching of students to colleges. We'll use that to anchor our rankings, and we'll see how that's done. Okay. But here's sort of the big idea. The big idea is that, okay, think about, why do we call it desirable rankings? So student I, there's some process, student I gets matched to a college mu I, all right? There's other colleges she may prefer. So think of some college C that she prefers to mu, all right? Okay, so C is ranked higher in her own preferences. So student I thinks that C is better than her own college, right? But in addition to that, right, college admissions are the outcome of some process, right? If I desire C, then presumably I was rejected by C in favor of some other student J, right? So and so in some sense, college C agrees with I that college C is the better college, right? I was rejected by Harvard. I went to Michigan. Harvard kind of agrees with me that Harvard is better than Michigan, right? And so this is sort of the basic kind of the sort of genesis of this paper. The basic foundational idea is that we want the following property to be satisfied. Any college that a student prefers to her own school should be ranked higher than her own school in the social ranking. Okay. So if I prefer C to mu, then C should be higher than mu kind of in the social ranking, and that should hold for every student. Okay. So we call this ranking by desire. Okay. And why is that? It's because we don't want to use preference. It's kind of an overloaded word in economics. So we're thinking of the schools that you prefer to your own. Those are the schools that you desire relative to your own. So we're going to call this ranking by desire. Okay. So this should, again, not be too foreign of an idea to try and use sort of observed outcomes to make inferences on preferences. Economists often do this. We generally call it revealed preference. But revealed preference is kind of the flip side of ranking by desire. Revealed preference says you are offered some things that you can choose from. So you got into a bunch of colleges. I got into Michigan, Wisconsin, Illinois. I chose Michigan. That reveals that Pete prefers Michigan to Wisconsin and Illinois. Right. So you can think about making a ranking based on sort of that approach, and indeed that has been done. There's a paper by Avery et al. In the QJE where they do exactly this. They take all of these sort of um, budget sets for every student. They see what school they pick, and they kind of aggregate that up into a social ranking that they call a revealed preference ranking of colleges and universities. Okay. So what's sort of the distinction between these two? I think this schematic kind of, I have to credit Thayer with drawing at some shows what's going on. So what a revealed preference ranking does is, so we observe that you are attending a college mu I, right? Revealed preference says, well, you got into all the red colleges, and so mu is better than everything in the red set, right? We're kind of doing the flip. We're kind of turning that on its head. Rather than looking at your budget set, we're looking at your upper contour set. So revealed preference as mu is better than everything in red. We're saying the things in blue should be better than mu. So we're looking sort of up your preference list. Revealed preference is looking down. And in sort of a longer seminar, I have a few slides where I kind of go into more detail about why we think desire is better than revealed preference. It's only 60 minutes today, so I kind of removed those, but I think maybe if we have some time at the end, we can come back and discuss that. But this is sort of the basic intuition. So Marion told me to pause for questions at a few times, so I think this is probably a good spot before I jump into the actual model. Okay. Then I guess we'll just keep going. So the model's pretty simple. There's a set of students and a set of colleges, I and C. These are just terminologies. These could be, other things. It could be, researchers in journals or whatever you want to rank. For 90% of the talk today, colleges are going to have a capacity of 1. Okay. At the very end, I'm going to basically tell you everything, not everything, but things go through to colleges with arbitrary capacities. But I think it's pretty instructive to really understand what's going on, to just first understand what's going on in the unit capacity case. So for most of the talk, colleges have a capacity of P is going to be a studentized strict preference ranking of the colleges, and there's going to be a matching mu. So a matching is just tells me who goes to what college, okay? And for our purposes, we're going to treat mu as just some exogenously given thing. Right? There's some process that goes on. People get assigned. It could be a centralized process like they do in Chile or lots of other countries. It could be a decentralized process like in the US. We could model this. It's not going to really matter for our purposes. So for the purposes of kind of calculating a ranking, we just take mu as an exogenous input. Okay. And our goal, remember, is to rank the colleges by using the student preferences. Okay, that's our goal. So what's a ranking? A ranking is just a weak ordering on the set of colleges. Okay, so I'll use this symbol for a generic ranking and kind of the weak part of the ranking. If I don't have the little bar underneath, that'll mean C is ranked strictly higher than C prime. But remember also, we are going to allow for tiers or ties, basically. So equivalently, you may want to think of a ranking as just an ordered partition of colleges. So pi 1 is like the best colleges. It's the Ivy League, right? That's the top tier colleges. Pi 2 is the second tier colleges. Cap K is always going to be the last tier of colleges, the lowest tier, the worst colleges. And so we're going to call the colleges in Pi K the tier K colleges. And similarly, the students who go to those colleges, they'll be the tier K students. Okay. All right. So now here, back to that property that we wanted. Okay, so this was sort of the motivation for the project, is that this is a property that we want our ranking to satisfy. For all students, all schools they prefer to their own school are ranked higher than their own school in the social ranking. Right? This was what we were hoping to achieve. You know, 5 minutes of thinking basically teaches you that this is impossible. And I'm going to show you an example on the next slide and then show how we can kind of fix this. Okay, so here's why it's impossible. Think about two states, A and B. So these are like geographic states. This is like, you know, Michigan and Ohio or something. So each state has two public colleges, a good one and a bad one. And each state has two students, a high quality student and a low quality student in state A and also in state B. Okay. And student preferences are constructed as follows. Within a state, the good school is preferred to the bad school by everyone, right? Everyone likes good better than bad, but good students want to go out of state. They want to get away from home, right? Bad students want to stay in state. Okay, so that's how I'm gonna put up a table of these preferences in a second, but let me just describe them in words first. College preferences are generally not going to play too much of a role in our results, but I think they're instructive here to kind of understand what's happening. So colleges are going to have lexicographic preferences where colleges want in-state students first, and then after that, high performing is better than low performing. So here's the picture. So if you look at, this is the good A-high, the high quality student in state A, right? She wants to go to school B. She wants to go to state B, but she prefers good to bad within that state, and then A good to A bad. The low quality student wants to stay in state A and prefers good to bad, right? On the right, I have the college preferences. So the college A good, right, prefers both A students and then both B students, and B good prefers both B students and then both A students. And let's say that, you know, we had the box assignment here. This was our matching. Okay, this was who got to go where, right? And this is, so if you wanted to use kind of stability as your equilibrium criterion, this is a stable assignment in this example. Okay. So remember, the property we want is this property that says every school that a student prefers to her own, which is the box assignment, is ranked higher in the social ranking. Okay, so this example is going to show this property is not possible. Because what does it require? It requires, think about student A high, right? So she prefers B good to her own school A good. So that means that B good needs to be ranked higher than A good. On the other hand, student B high prefers A good to her own school B good. So this property would require that A good needs to be ranked higher than B good. And that's going to be a contradiction. So this doesn't work. Okay. Okay, so because end the talk here, it doesn't work. But we can think about more about why is it not working. Okay, so it seems pretty clear that it's unanimous here that A good should be higher than A bad, and B good should be higher than B bad. Everyone agrees, right? So it seems like the right ranking is probably to put the good schools in tier 1, the bad schools in tier 2. Okay. And what's really driving this sort of failure that we saw on the last slide is that this initial assignment here is actually Pareto inefficient, and it's Pareto inefficient due to the college choices, right? The colleges are selecting their students, and the out-of-state students aren't getting into the in-state, the A students can't get into the B colleges, right? So that really leads to an inefficiency. So if you look at this, students A high and B high, they would want to trade their assignments, right? That would be better for them. So Pareto inefficient from the student's perspective. When I say Pareto inefficient throughout the whole talk, I mean from the student's perspective, right? Because we're trying to aggregate student preferences. Our goal is to rank colleges based on student preferences. So we're going to focus on the student side. So let's imagine for a second, you can't just trade, your college admissions letters. You can't just say, oh, I got into school A and you got into school B. Let's just, swap our letters and go on our merry way. That's not how college admissions works. But let's say that you could do that, just as a thought experiment, right? So if we allowed students to trade, we would get the green assignment here, right? The A high and B high would trade their schools, and we would reach a Pareto efficient matching. So we call matchings like these, we call them shadow matchings, because we think of them as sort of the outcome of some sort of shadow economy where people are trading their college admissions, okay? And so now notice that relative to this shadow matching, which I'll always note with a star, this actually does indeed satisfy the property that we want. Everything that's ranked higher than your shadow matching is ranked higher in the social ranking. This ranking here works, right? Because for the high students, there's nothing better than their shadow matching. So they don't desire anything. relative to their shadow matching. A low, he desires A good to A bad, but A good is ranked higher than A bad. And B good is desired to B bad for B low, and B good is ranked higher than B bad. So what's kind of happening here is that it's Pareto efficiency is going to play a big role in our results, and Pareto inefficiencies kind of screw things up. So kind of fixing the Pareto inefficiency, at least in terms of constructing a ranking, we kind of think of this as kind of removing, there's some desire that was sort of idiosyncratic due to sort of these idiosyncratic preferences to kind of go out of state in this example. And so if we kind of fix that and remove the Pareto inefficiency, things will work. Okay. And we'll show that this actually works not just in this example, but we'll show how to do this in general. Okay. So here's the general condition, or the general axiom that we will use. So this is the thing that I wanted in the beginning, right? This is the one that doesn't work, right? This thing in brackets up here. This doesn't work. And it doesn't work. What does it mean? We have to strengthen our preference condition. We need to strengthen kind of the antecedent of this statement here, right? Oops, sorry. Wrong way. Okay. So we're going to do this in general by introducing what we call the shadow match, which is going to be a generalization of what I call shadow matchings. So a shadow matching is just a Pareto efficient Pareto improvement of the initial matching mu. Okay, so we have an initial matching mu, and then we have a Pareto efficient Pareto improvement. That's our shadow matching. And we're going to say that a student desires a college if it's preferred to her shadow matching. Okay. So we're using the word desire because this is kind of like stronger than preference, right? So desire is a stronger condition because clearly if you desire something to your shadow matching, you also prefer it to your original matching. So it's kind of a strengthening of this first part up here, okay? And then weak desire, just replace, the strict preference with the weak preference. It's called weak desire, okay? But it's still relative to the shadow matching. And with this definition, we can state our first axiom, which is we call the axiom of desire. So we say that a ranking satisfies the axiom of desire if there exists a shadow matching mu star such that for every student in every college that I desires, we have that college is ranked higher than mu star. So it's essentially just this thing in brackets up here, but just replace the mu with the mu star. Right? Everything you prefer to your shadow matching is ranked higher in the social ranking. Okay. I see there's some things going on in the chat, and I don't know. Hopefully Thayer is taking care of it all. But if not, please speak up. So this is just this is just showing in that example that the axiom of desire works. I kind of already talked through this, and so I think I'll just kind of skip through this slide. It's really what I just talked through 2 slides ago. It's just showing that, A low desires A good. That's our shadow matching, and indeed this condition holds for A low, and it holds for B low, and the high students don't desire anything because nothing is preferred to their shadow matching. So the axiom of desire holds vacuously there. Okay. So that's the one key axiom. It's not going to be quite enough to get what we think is a reasonable ranking. And here's the motivation for what is going to be there's going to be 2 axioms, and this is the second one. So the second one we call justification, and here's what it's all about. So think about this example here. There's 5 students. Everyone has the exact same preferences, except for this guy 5, right? Everyone prefers A to E in that order, except for guy 5 who prefers school E. Right? And this is our matching. So this is the unique Pareto efficient assignment here. This is the unique shadow matching. And if you look at this, right, nobody's ever going to desire school E, right? School E is not above, it's very low in everyone's preferences except for this guy. So nobody ever prefers anything to school E at any shadow matching. And so what that means is the axiom of desire kind of tells us nothing, right? It has no bite here. But it seems like probably what's going on in this case is this guy 5 just kind of has his own sort of idiosyncratic preferences for school E. Maybe school E is very close to his home and he wants to stay nearby, right? So it seems like in this example, the right answer would be that E should be last. But the axiom of desire doesn't really give us that because there is no desire. Nobody desires this school because it's so low in everyone's preferences. Okay? So we need, the axiom of desire says if you desire something, it should be ranked high. We sort of need the converse of that too, right? We need that a school should be ranked high in a higher tier only if it's desired by someone in a lower tier. So we kind of build this up from the bottom, right? If nobody desires C, then that's like our school E in that last example, right? Over here, nobody desires school E, it should be ranked last. And then we just kind of build up from here, right? If only students in the last tier desire C, then C can be ranked second to last, right? And so forth, so on and so forth. So this is here is the formal definition. We say a college's ranking is justified if either the lowest tier is justified automatically. So I don't have to justify putting you in the bottom, right? That's automatically justified. But if I want to put you higher, then there has to be a tier. If I want to put you in tier K, right? If I want to put you in tier 5, then there has to be either a tier 5 or tier 6 college that has already been justified, and that student weakly desires C, right? So if I want to put you in tier 5, someone from tier 6 better desire you. Otherwise, I should put you in lower in tier 6. Okay, and we'll say that a ranking is justified if every college's ranking is justified. Okay. All right. So then we're going to call a ranking desirable. Just to have a short word for it. If there exists a shadow matching that's such that mu satisfies the axiom of desire and justification. Okay, and I just saw in the chat someone asked something about can there be multiple shadow matchings and what do we do there? Many of you may be having that question right now, and indeed there can be, and that's a good intuition. But it's going to be a big part of the last half of the talk, and I'm going to show you a sense in which it doesn't matter. Essentially, I'm going to tell you no matter what shadow matching you use, everything kind of converges to the same thing as the market grows large. So there can be multiple shadow matchings, but it's not going to be a big deal. Okay, so just a little foreshadowing. Okay. So let me, so those were our initial axioms, okay? And maybe you like them, maybe you don't. We just kind of, we think they make sense, but, we realize we invented them. So if you don't like them, let me connect it with something that you probably do like, hopefully, if you're an economist, which is competitive equilibria, okay? And so this was motivated by one of our referees who asked us, well, let me just say, what is a competitive equilibrium, right? So in standard textbook economics, a competitive equilibrium is prices and allocations such that every agent's allocation maximizes utility given their budget and markets clear, right? That's what we tell our undergrads, okay? And one of our referees asked us, he was like, well, okay, there's this paper by Richter and Rubenstein in the AER about 10 years ago where they generalized competitive equilibria to really abstract settings, right? So in typical Rubenstein fashion, it's a super abstract paper. There's a lot going on in that paper. I'm only going to give you the small part of it that is really relevant for us. But essentially what they do is they generalize competitive equilibria to just orderings over alternatives, because if you think about it, orderings are kind of like prices. You can kind of think of prices as like, higher ranked things have higher prices, right? So here's how their model of competitive equilibrium works, and then I'm going to show you how it's connected to ours. So agent I has an endowment mu. This is like her matched college in our example, okay? And so if you think of rankings as kind of like prices, every ranking induces a budget set. You're endowed with something, there's a ranking, you can afford everything that's ranked lower, right? That's your budget set. And so then an allocation and a ranking, right? Just like a price is an allocation and a ranking is a competitive equilibrium if everyone's allocation maximizes their preferences given their budget. And this is just the condition in our one-to-one setup. No two people have the same demand, right? Everybody demands a different school. This is essentially market clearing, okay? And so Richter and Rubenstein introduced this, and they want to interpret this ranking as a type of social prestige, which kind of sounds like exactly what we're doing, right? That's sounds very similar. And our referees asked us, well, okay, what's the connection? There must be some connection. And indeed, we looked at this and we did find that there is a connection. So to introduce this connection formally, I need to introduce one other property of a ranking. So remember, in general, we rank relative to a shadow matching mu, which is not your initial matching, right? But you may think another natural requirement for rankings is that your shadow matching should be ranked the same as your, original assignment, right? If you think of college, assignments as roughly assortative, right? And I go to Michigan, then sort of I'm like a good, public college student. You may think that, schools like Michigan, Wisconsin, Illinois, that's sort of my tier of colleges. Those should all kind of be ranked, the same, but maybe Harvard should be a lot better in a higher tier, right? So if you think of that, you may want to require that our ranking should be connected, what we call connected to the original assignment. And we say ranking is connected if the shadow matching and mu are in the same tier for all I. Okay? And so then with that definition, we have a result that a ranking and a matching are a competitive equilibrium if and only if the ranking satisfies the axiom of desire and is connected to mu. So it's kind of saying an equivalence result between competitive equilibria and the axiom of desire. And what's happening, it's pretty intuitive, right? With connected, you can afford your shadow matching, right? Because it's in the same tier, so you can afford it. But by the axiom of desire, everything you prefer to your shadow matching is ranked higher, so everything you prefer is unaffordable. So that means that your demand has to be your shadow matching, right? And so then we have a competitive equilibrium. So just that doesn't make you didn't get the details there. The high level takeaway is that there is an equivalence between our axioms and competitive equilibria under this connectedness assumption. Okay. Now, if you think just about competitive equilibria, there is generally a problem with competitive equilibria that carries over here, which is that competitive equilibria are in general not unique. Right? This happens, we know this problem well, and it happens also here. But this becomes problematic if we want to interpret this as prestige, right? Because we could have two competitive equilibria that have opposite rankings of prestige, right? So which is more prestigious, right? How do we decide? And so if you notice in this last theorem, I didn't use justification. It only requires the axiom of desire, and it turns out that justification is what gets us out of this kind of conundrum. And justification in a competitive equilibrium world, it can be thought of as a type of kind of inflation. Very different from kind of, the inflation we've seen in the news, but what we're going to call inflation, we're going to say that the rank of a good is inflated if we can lower it and demands do not change. So here I have two rankings, right? On the left and on the right. All that's happened here is the ranking of good B has been lowered, right? If in the competitive equilibrium world, I do this and I get the exact same demands on the left and on the right, then we say that the left has an inflated ranking of good B. I don't want to go too much into the details here because this is not like a big part of our talk. This is really sort of a side thing. But what we can show is that a ranking is desirable and connected to mu if and only if it's a competitive equilibrium with no inflation. Okay. So we have kind of a side paper where we delve into all of the details about this, and so I've really skimped on the details here, but I just wanted to get the high level result out there that we do get if we have this desirability as I've defined it and connectedness, we actually are able to pin down a unique competitive equilibrium without inflation. Okay. All right. Okay. So now that I've given, maybe that's a good spot to pause. So now I'm going to move on to actually show you how we construct desirable rank. I'm going to use some algorithms for doing it. Okay, so I'm going to give you two algorithms for constructing desirable rankings. Okay, their names are here, and I'm going to start with number one, as we do, called delayed trading cycles. So delayed trading cycles is based on the top trading cycles algorithm of Shapley and Scarf. That's why it's called delayed trading cycles. And I give this talk to various audiences, and some people, top trading cycles in like my corner of the world is like super well known. Everyone, knows all about it, but sometimes people don't know it. So I'm going to go over just the basic top trading cycles and then give you how we're going to use it. And here's the definition in words, but I think an example will be better. So top trading cycles, what happens? The input to top trading cycles is an initial matching, Okay, so that's the boxes here. And it's a pointing algorithm. So what happens is every school points to the student that owns that is assigned there, and students point to their most preferred school that's in the market. So here, school E belongs to student one, right? So E points to one. One's most preferred school is A. One points to A. A is assigned to five. So A points to five. Five's favorite school is B. Five points to B. And we just keep going. And eventually we get a picture like this, which has a bunch of cycles. Okay? All right. So what top trading cycles then does is it removes the cycles. There will always be at least one cycle. We remove the cycles. Okay, we have two cycles. We get rid of them. And then we just keep going, right? So now one school she was pointing at is gone. Her new favorite remaining school is D. So now 1 points to D and 3 points to C. We have another cycle. Remove that cycle. And now 2's favorite school that's left is E. We have our final cycle. And we've computed, these are called the top trading cycles, right? We've computed all of these cycles, okay? So that's top trading cycles. And in a typical implementation of top trading cycles, if you're doing school choice or something, what you do is you make all these trades. You implement the indicated trades, and then we reach a Pareto efficient assignment, okay? We're not gonna do that. We're gonna do something else. What instead we're gonna do is we're going to instead construct our ranking by ranking the cycles. Okay, that's going to be basically the idea of the algorithm is let's rank the cycles, right? So this has been an algorithm that's gone, it's been, 50 years since it's been around. As far as we know, we're the first kind of people who thought, well, there's information contained in this sort of ordering of cycles. We should use that information. And so we're going to use that information to construct a ranking. And it's not going to be in sort of the naive way where we just take all the top cycles and rank them first. What we're going to do is we're going to sort of rank cycles kind of in a slightly more intelligent way. And we're going to introduce this idea of what we call a last cycle. So a cycle is a last cycle if there's two equivalent definitions. If there exists a cycle selection order in which it is chosen last. So in that example that I just gave you, as soon as a cycle formed, I just took them away. And that's usually what you do in top trading cycles because you're not worried about cycle selection. But you don't need to do that. You can select cycles in any order. Once a cycle forms, it always stays around until you remove it. So if there's a way to choose cycles where that cycle you're thinking about is chosen last, we call that a last cycle. The other way to think about a last cycle, which is an equivalent definition, is that no student outside of the cycle desires any school inside the cycle. So these are going to be the same thing. And I think maybe, again, a picture is worth 1,000 words, right? So we have our cycles, right? These are the cycles we found. And so now what I'm going to do is I'm going to draw these dashed arrows. These are kind of like my desirability arrows. So I'm going to draw a dashed arrow if you desire something outside of your cycle, right? So student one, right, his TTC school is D. He desires A and B. So I draw a dashed arrow from A to B, from A and to B, right? Student two desires A and C. So I draw a dashed arrow from A to C, from A to C. Et cetera, et cetera. And so I have this sort of, these arrows pointing from, later cycles to earlier cycles, right? And you can never have an arrow pointing from an earlier cycle to a later cycle. That's just by the nature of top trading cycles, that will never happen. So these dashed arrows will never cycle. And now the thing to note about this is that there's some cycles that have a lot of arrows coming into them, like this one. These are sort of the more desirable schools. There's some cycle that, like this one over here, that are kind of lonely. Nobody's pointing into that cycle, right? Nobody wants school F besides student 6. Nobody outside of this cycle wants this school, right? So there's no incoming arrows to this cycle. This cycle down here also has no incoming arrows. Nobody wants anything, no student outside of the cycle wants anything in the cycle. So these are our last cycles, right? They're the ones with no incoming arrows, okay? So what do? We find this is intuitively kind of the undesirable schools, so we rank them last, right? And then we repeat, right? We have the remaining cycles, we draw our desirability arrows. This one has no new incoming arrows. We rank it second to last, and this is my final ranking, right? So this is the delayed trading cycle algorithm. This is how it works. Okay. All right. So here's the formal definition. I don't read it. I'm going to skip that. It's not worth it. Here's just another picture just to show you in a more complicated example, right? We call this things like this. We call them desirability graphs. And what is happening here is every node in this picture represents a TTC cycle. So every node represents several schools. And I just do the same thing. I draw arrows. If someone outside of this, someone in the cycle prefers a school to the other cycle, right? So if someone in this cycle prefers a school in this cycle, I draw an arrow. And there's always going to be these cycles on the bottom that kind of have no incoming arrows. That's the big red ones. So I move them down. I rank them last. Now I have some new last cycles, right? Move them down, rank them last, and I just keep going, right? And that's my delayed trading cycles. Okay. All right. So here's the theorem about it. This is a desirable ranking of the colleges, and also it's connected to mu. Okay. So for desirability, right, we need to think what is the relevant shadow matching. The relevant shadow matching here is the TTC matching itself. Okay. And so why does this satisfy the axiom of desire? Well, it's just colleges you desire, they're removed earlier in the running of top trading cycles, right? The things that you're pointing at outside of your own cycle, those are the things you desire. And so that's exactly how the algorithm is constructed. Right? For justification, also pretty simple, right? So the bottom schools are justified anyway, but think about the second to last tier, right? If you weren't in the last tier, why weren't you in the last tier? It's because I didn't remove you first. There was someone pointing at you. So someone in the last tier desires you, right? So then it's justified to rank you second to last, et cetera, et cetera. And for connectedness, right, your own college and your shadow matching are in the same TTC cycle, and so they're ranked the same. And so this is a desirable and connected ranking. Okay. Okay, so that's our first algorithm. I have a second algorithm, which is actually even simpler than the first one. So we call this algorithm the iterated removal of under-demanded schools. Okay, so the idea here is, again, we have an initial matching, and let's think about a shadow matching mu star. Okay, we're going to call a college under-demanded if for every student she prefers her shadow matching to C, right? So the under-demanded schools are just that. They're the schools that nobody wants relative to their shadow matching, strictly, right? So this is a weak preference here, right? So essentially it's saying no student prefers C to their shadow matching, right? And then the algorithm is super simple. It's just take the original matching, find the the original shadow matching, take the shadow matching, take the shadow matching, find the under-demanded schools, remove them, and then repeat. That's all it is. It's the whole thing, right? Find the under-demanded schools, rank them last, and then just sort of find the new under-demanded schools and repeat. Okay. So the picture is actually very similar. It has a slightly different interpretation where now, rather than each node being a cycle, each node is an individual school, and I draw an arrow again if you desire the school you're pointing at. But otherwise, the intuition is this are very, very similar algorithms, and I'll give you a sense in which they're the same in a few slides. Okay. But here's how it works on this little example. So our red matching, say, is our shadow matching, right? If you look at this example, think about school F, right? For every student, F is weakly below their shadow matching, right? So F is under-demanded. Similarly, for every school D is below every student's shadow matching, right? So D is equal to his shadow matching for this guy, and it's below for everybody else. So school D is under-demanded, school E is under-demanded. Notice that school C, for instance, is not under-demanded, right? E, this guy actually wants school C. He prefers C to his shadow matching. So C is not under-demanded, neither are A or B. Okay, so that means that the under-demanded schools are D, E, F. That's my bottom tier. Once I remove them, right, now I have the smaller market. Here, B is not under-demanded because this guy 3 desires B, but A and C actually are under-demanded. So our next tier is AC. Okay. So if we remove AC, and then we have B is last, so B goes first. So our iris ranking is B, AC, D, E, F. And just as a point of comparison, right, this is not the same thing as the DTC ranking. I'm going to tell you a sense in a second, which just doesn't matter because, as the market grows large, everything becomes the same. But in small markets, they can indeed be different. They will both be desirable. Okay. So it turns out that any IRIS ranking is a desirable ranking of the colleges. The intuition is pretty similar to what the DTC intuition was by that desirability graph. I think it makes it really clear. So I'm not going to spend a whole lot of time on that. But they, in general, are not connected to mu. So that's sort of one distinction between these, is that these are not connected. Okay. But they are kind of very, very similar algorithms, right? They have very similar flavor of sort of identifying the bottom schools, ranking them last, and building it up. And the distinction, and so in terms of, and it turns out that when the initial mu is Pareto efficient, then in fact they are indeed equivalent. So if the initial mu is Pareto efficient, then you're running delayed trading cycles on a Pareto efficient assignment. It seems kind of silly because you're just going to get a bunch of self cycles, but you want to know about these, who are the last cycles, so that there is information contained in there. And it turns out that this becomes the same thing as just doing the removal of under-demanded schools when the initial mu is Pareto efficient. When it's not, then we have to sort of first Pareto improve to our shadow matching, and then maybe we can get something different. It turns out that delayed trading cycles is not only desirable, but is actually the unique desirable ranking that is connected to mu. So if you remember our results on competitive equilibria, this is actually the unique competitive equilibrium ranking without inflation. And we can also say that if we strengthen the justification a little bit, the IRIS ranking is the unique, desirable, and what we call strongly justified ranking with respect to mu star. So I'm going over this a little bit fast because I want to get to the next part, which I think is the most interesting part of the paper, and I only have 10 minutes left. But this is like a slight strengthening of justification. In the original justification, you could have been desired by someone in your own tier that was already justified. Here I'm saying you have to be strictly desired by someone in a strictly lower tier. So see the paper if you want the details of that. I don't want to spend too much time getting into that right now because I want to tell you the next part, which is I think the most interesting part of the paper, which is the convergence result. So I've given you a bunch of methods for producing desirable rankings, or two. I've given you two, but in fact there's many because there could be many shadow matchings, right? So how do we choose? And my answer to you is going to be, it doesn't matter, okay? And so we're going to state that in a formal sense. Here's the informal sense. It doesn't matter in the sense that as the market grows large, any desirable ranking converges to the so-called true underlying ranking of the colleges. I haven't told you what true means yet. I'm going to do that in a second, but this is kind of where we're going. So if you don't, I don't get through the full, rest of the slides, hopefully at least you have the takeaway that it doesn't really matter which of these algorithms and which shadow matching you use. If the market is large, they're going to all be basically the same. Okay. All right. So how are we going to, what do I mean by true preferences? I need to augment the model a little bit. So let's model student preferences as follows. So a student has a utility for a school C that is a linear combination of a theta, which is like a common quality. So everyone has the same theta for school C, and then an idiosyncratic part, that's eta, right? So theta is like vertical preferences for quality. Eta is like horizontal preferences for, say, location or something, right? And then alpha is just the weight we place on quality. All the thetas and etas are drawn uniformly IID. The uniform distribution is not important here. That doesn't matter. We can relax that. The IID part is very important, but the uniform part is not. Okay, so what do I mean by correct rankings, or true rankings, right? We're going to say ranking is correct if C is ranked higher than C prime, if and only if it has true higher quality. Theta C is higher than theta C prime. Okay, so it's easy to construct realizations of random variables where we screw this up, right? If people have really high draws for the idiosyncratic part, then that can sort of overwhelm the common component, and we'll be wrong, right? But if we have a good ranking method, this should be rare. It should be a rare occurrence, and so we're going to formalize that. And the easiest way to formalize it is to think about the percentile ranking. So a percentile ranking is exactly what you think it is. It's just the percentage of colleges you're ranked ahead of. Right? This is the number of colleges that are ranked ahead of you. You're ranked ahead of, sorry, and we just turn that into a percentile by dividing by the total number. Right? Since our thetas are uniform, right, as the market grows big, right, we're sort of filling in the unit interval, right? So if I'm a college that has quality 0.7, as the market grows large, my percentile ranking should be about 70th percentile, right? So my rho should be about equal to my theta, right, as the market grows large. Okay. So to be a little bit more formal, let's take any small epsilon, right? And we're going to let C of epsilon, we're going to think of theta at C as a college's target ranking. And we're going to think of these colleges, these are the colleges that are ranked within epsilon of their targets, okay? So these are the colleges whose calculated ranking is within plus or minus epsilon of their true quality, right? And so for all these colleges that are in this set for any given market, we'll say their ranking is epsilon correct, right? They're correct up to epsilon. Okay. Then the formal result is as follows. So if we have a desirable ranking and it's induced percentile ranking, then for any epsilon, as the market grows large, all college rankings are epsilon correct. So a little bit more formally, if we take the expected number, the expected percentage of the colleges whose rankings are epsilon correct, the expected proportion of colleges whose rankings are epsilon correct, and then take the limit as n gets large, this goes to 1. So in the limit, all colleges have rankings that are within epsilon of their true quality. Okay, that's the result. So this is what I mean when I say it doesn't matter which one you use if the market is large enough. So this holds for any shadow matchings or is all that we need is a desirable rankings. We have many possible ways of calculating desirable rankings, many possible shadow matchings. They all converge to the same thing. Okay. There's part of this proof also shows this kind of theorem, which I think is good in its own right to highlight, which is that you might be worried that we're allowing for ties. So maybe just, everything is just flat and that's not a useful ranking. We just have like a couple of big tiers or something. And what this result says is that is not true. It says essentially that the size of the largest ranking as a percentage of the market size becomes small in the limit. So the size of the largest ranking converges in probability to 0. Okay. So now my question is, I have 5 minutes. Do I want to talk about the proof technique or do I want to talk about the multi-capacity? The proof is very cool. So maybe I'm not going to go into a lot of detail. If I have 90 minutes, I would talk about this a lot, but it's a very cool idea. So I want to spend at least a couple of minutes talking about it because it relies on this really innovative technique of Sang-Mak Lee in his job market paper, where he uses a result from random graph theory in a very clever way. So think about a graph here. This is not like the matchings. This does not denote match. So okay. So a bipartite graph. What is it? It's a graph that has nodes on 2 sides, right? So think of this as schools and students. Okay. And so this is just a random graph. So a random graph is where we just randomly draw, edges between pairs of nodes, IID with some probability p. So this does not really represent like the matching mu that we've been talking about. This is just a random graph where people are connected, IID, probability p. And so what Sang-Mak realized is that we can use this results from Dewande et al. On random graph theory. And their result is that as the size of a bipartite random graph gets large, the size of the largest balanced biclique is small. So what's a balanced biclique? A balanced biclique is a complete connected subgraph. So in this picture, the green set is a balanced biclique. Everything in this green circle is connected to everything in this green circle. So that's a biclique, and they have the same size, so that's a balanced biclique. Okay, and what this result shows is that as this is just a pure graph theory result. Okay, so it says as the graph gets large, balanced bicliques become small. Okay, and what Sang-Mak realized is we can use this in a very cool way for lots of things. So we can basically use this to show that something is unusual by showing it corresponds to a biclique in a corresponding random graph. So he uses this for stable matchings. we're going to use this for desirable rankings, but I think this is a very useful proof technique that you should be aware of. It's a lot more complicated than what I'm going to present to you in this one slide, but I think there's something that you might be able to make use of. So you should go read Sangmak's paper or our paper if you're interested in more of it. And so what's happening in our case is that we expect it should be unusual for a theta C college to be ranked much lower than its true quality if our ranking is desirable. Why should that be unusual? Well, if the ranking is desirable, right, there's students at colleges who are ranked above you, but they don't desire you. So imagine I'm a 0.7 quality college and I'm ranked in the 50th percentile. Then there's students at colleges who have lower true qualities than me, and they're ranked higher, but they don't desire me, right? That seems weird. And the only way that can happen is if those students have low idiosyncratic utilities, okay? And in a large market, it should be unusual for all the students to have low idiosyncratic utilities. Someone's going to randomly get a high draw for me, and I have a high true quality, so someone's going to desire me, which is going to break my ranking, right? So formally what we do is that we draw a random graph. We fix some threshold. We draw a random graph where a student and a college are connected if they have a low idiosyncratic utility, if eta is less than this threshold. Right? And then what we do, and this is sort of where all the work comes in, is you show that students at nearby overranked colleges, they all have to have low draws for the underranked colleges. So this means that they're all below this threshold, so they're all connected in this random graph, so they form a biclique, and then the biclique has to be small. So there can't be too many of these colleges who are underranked, okay? I know that probably went by really, really fast, but I encourage you to go read Sangmak's paper. It's super cool, and probably very useful beyond just this. I only have 2 minutes left, so I have to pick and choose here. So if you don't, if you're more of a visual learner, right? We have some simulations to basically confirm this result. So what's happening here, let me go to the bigger picture. On the vertical axis, we have true college qualities. On the horizontal axis, we have calculated percentile ranks. So if things are correct, we should just be totally along the 45-degree line, right? And we see that's kind of what happens, right? When n is small, right, we're sort of not ranking very well. As n gets bigger to 10, 30, 50, by the time we're at 100, we're basically lined up along the 45-degree line, okay? And we have 500, it's even better, right? And so here's just some more simulations, basically confirming that for high n's and high alphas, when alpha is low, it takes longer to converge, but eventually we do. I'm going to skip this. I just want to say a few words in my last minute about multi-unit capacity. I'm not going to say much because all I'm going to say is essentially now allow colleges to have arbitrary capacities, right? The whole talk we've been talking about capacity 1, pretty much everything continues to go through. Well, okay, I shouldn't say pretty much everything. Enough goes through to make things work. So it turns out that in this case, delayed trading cycles is no longer well defined because TTC is no longer well defined with multiple capacities. It's unclear which copy of a college you should point to. And so this essentially means that this is related to the fact that there will not exist a desirable and connected ranking. But thankfully, the iris algorithm works great. It still works fine. It's still exactly the same. You just choose a shadow matching, identify under-demanded colleges, rank and repeats, and we have the exact same convergence result goes through. With multi-unit capacities, any iris ranking is desirable, and for any shadow matching, as the market grows large, the iris ranking converges to the true underlying ranking of the colleges. Okay, so just I know I went through that again really, really fast. 60 minutes is just not enough time for this talk. There's too much, but just be satisfied. Most of the talk was single seat, but everything still works with multiple capacities. Since I'm out of time, let me skip this and let me just go to the conclusion. There's not much new on the conclusion slide, just to say that we introduced this new ranking method based on this idea of desire. We give you some algorithms, we show they converge to the true ranking, and hopefully in a few weeks, I can give you some actual rankings data from Chilean colleges. And that's it. Thank you very much.